Hello, welcome back. So in today's episode, we will cover a SPSC, or single producer, single consumer, lockless queue. So I like to think this is a fairly standard pattern used in low-level or system-level programming. So as name implies, right, it's a single producer, single consumer lockless queue. So you can't have more than one producer or one consumer. It's only one producer and one consumer at any given time. But the data structure does allow you to sort of move the producer and consumer to different execution context, or really CPUs, if you need to. But anyway, in any given time, only one producer and one consumer. So this is a fairly common pattern using, for example, in drivers. When you interface with ASIC, there's typically or sometimes basically an access interface that you can interact with, right? And then this would be sort of the similar interface that you would implement. So the nice thing about this is as implied name, you don't actually need a mutex to work with it, right? So long as you, access the data region or the control region in a certain defined order, you have like the implementation will be correct, right? I do want to highlight those. So in this episode, we will focus on the logical implementation of a SPSC lockless queue. On a real implementation, you need to be careful about basic memory barriers and ordering effects, right? And then the modern CPUs are designed in such a way that the executing context will always perceive the sequence of commands to be executed serially, perceptually. But when you look at it from another CPU, the instruction might appear to execute out of order, right? And then so this is where weak memory ordering, strong memory ordering comes in. And then so when you do this on, for example, the ARM architecture, you usually need to insert barriers to make sure that the orders are perceived correctly across cores. So we're not going to worry about that in this episode. We're going to assume logical sequential ordering for this example here. And so with that out of the way, so let's dig into a look at the actual implementation a little bit, or the design. So as mentioned before, right, so the SPSC queue, lockless queue, is assumed to be executing under two different executing contexts. So you have a write pointer and a read pointer, right? And then so the read pointer is owned by the consumer, right? So the consumer can advance the read pointer. And the write pointer is owned by the producer. And then so the producer can advance the write pointer. That said, they could look at each other's pointer, right? So then the producer can look at the read pointer. It cannot modify it, but it can look at it. And similarly, the consumer can look at the write pointer. It cannot modify it, but it can look at it, right? And then so basically, when the two pointers overlap, the system is in a state where the queue is empty, right? When the write pointer is next, so write pointer plus 1, modulus the size, right, equals the read pointer, then the queue is full, right? So I guess the tricky part of a SPSC lockless queue implementation is really all the possible interleaving execution that could happen between the two different contexts, right? So the write pointer would, the other thing to keep in mind is, so when the write pointer writes and advances it, and the read pointer tries to read, how do you know what's the order between the two of these events, right? Is what if the reading is happening when the write is just happening at the same time? What if the read happens right after the write? What if the read happens after the write has written the data but has not advanced the write pointer, right? So all these interleaving sequence of instructions between two different executing contexts, we need to make sure that under all these interleaving scenarios, the system is in a coherent state, right? And then if it has to fail, it fails in a correct or safe fashion, right? So in this example, we will be using +cal to sort of specify our specification, right? So +cal is it's more of a C-like syntax, and then you use a pcal command to sort of transpile it down to the native TLA plus notation. So yeah, so as you can probably imagine, right, like basically every single instruction that we specify here is its separate state, right? And then so maybe I'll take a look at example on the left here, or sorry, maybe I'll go down here. Yeah, so basically, as the reader, the first thing we want to do is want to make sure there's something to read, right? And then so we check for empty. And then this itself is an atomic operation, right? Actually, there's more, right? There's like loading the memory, the memory value from the read pointer into the register, loading the memory value from the write pointer into another register, then do the comparison, right? But then for the simplicity, we can model that as an atomic instruction here. So the atomicity in a PlusCal specification is basically the delimiter is a label, right? So anything under the same label is assumed to be atomic, and that's why you see label being basically peppered over the place to ensure that we have the finest granularity, right? I believe that the loading the value from memory into register for the read pointer and the write pointer, that doesn't matter in the context of this discussion, and then so that's modeled as a single atomic instruction. But basically, checking for emptiness, right? And then if it is empty, then we early return that this is now an atomic operation itself, right? Reading the buffer is an atomic operation, right? Clearing out the buffer is another atomic operation, right? And the updated read pointer is yet another atomic operation, right? And then so now contrast that to so the symmetrically, right, on the right point on the writer side, these are the things that we need to check. We need to check that we're not full, right? If we're full, we need to early return, right? And if we're not full, then we can update to the right buffer, right? And then finally we can update the right pointer, right? And then any of these labels down here can interleave with any of the labels up here, right? And then so some of the more complex scenario, as you can imagine, would be the right pointer completely overwhelms the read pointer, right? We write, and then we wrap around the queue and then go way to the back, and then we caught up with the read pointer, right? It can happen the other way as well, right? Like the write context is somehow stalled, and the read pointer read, and then caught up with the write pointer, right? And then what if they're chasing each other at the same time, right? And then so all these are possible scenarios that in all interleaving scenarios, the system has to behave correctly, right? Okay, so so with that out of the way, let's take a look at some of the safety properties we want to ensure, right? So for safety property, both reader and writer can access their critical section at the same time. That's okay, so long as they're not accessing the same index or the same element, right? They can operate on different portion of the array. That's okay. But then if they're both in the critical section, they cannot be operating on the same pointer or same index. And then for liveness, for example, we want to make sure that the queue never hangs, right? So every index in the array should be used and unused, and used and unused, and then continue cycling, right? So as the SPSC queue sort of advances into state, we're using every single element and then releasing every single element, right? So that's the liveness property that's defined here. So at least for me, right, like if you ever worked on these kind of lockless data structures, they are very tricky to get right? Like in the absence of TLA plus, trying to do this, catch all the possible events using unit testing is very challenging, right? Because a lot of this really depends on the scheduling, right? How busy the system is, right? Like you can't really force the scheduler or force the system to sort of iron out certain corner scenarios, right? Like you may be running the SPSC, your implementation of it, for like days, and everything will be fine. and then until somebody spun up like some really CPU hungry process start starving your implementation, and then things will start breaking, right? And then so these are the kind of things that we really don't want to discover, I guess, late in the cycle in production environment, right? Like we want to get it right? And this is the magic of TLA Plus. Right? This is why I believe this is an extremely useful tool to sort of iron out all the boundary, all the corner cases of your design, right? Okay, so with that out of the way, right? And then so now let's take a look, right? So okay, so I need to do this here, right? So since for this particular specification, it was specified using PlusCal, and then so you can consult other sources, but basically your PlusCal source is captured sort of like a comment in your specification, right? And then so basically everything here is part of the PlusCal specification, and then so this is the PlusCal notation. And then once you have that, you want to do pcal, on your specification, and then this would generate this would transpile your PlusCal source down to actual TLA native notation. So that's this stuff here. So this stuff that I'm highlighting is all auto-generated by the transpiler. So once that's done, you can actually start verifying your algorithm, right? Or you should use the model checker to verify your specification. Okay, so it passed, but just to prove the point, right? Like, how do we know, like, does it actually work, right? And then so I'm gonna go here, and for example, I will swap the critical section line with the pointer update, right? So now we update the repointer first, and then before we actually read it, right? Just as a bug, right? So again, right, like in a real system, depending how the CPU depending on how the executing context, the read and write contexts are being scheduled, like modern CPU are like amazingly fast, right? Like these are probably resolved to like a few instructions, right? And then so it is entirely plausible, if you make this mistake or in your design, using C or C++ or Rust or whatever language you're choosing, it may just appear to work, right? Like you need to hit a window where like, really the two executing contexts are interleaving at the most inconvenient time, then you get the bug, right? And then so this is simulating that, right? So, I'm just gonna accidentally swap the two instruction here where I'm bumping the repointer first, then I'm gonna access the content, access the value, right? So with that, I try to run it, and then boom, right? TLA Plus says, oh, the model checker says, wait a second, you have a bug, right? And then so if you sort of walk the stack trace backwards, it should tell you where it went wrong. And then similarly, right? And then so if I do the same thing, right? If I swap these two, so instead of doing swapping the read, I swap it on the right side, right? So I bump the right pointer before I update the critical section. Yeah, then I see the same problem, right? Yeah, so hopefully this sort of highlights the usefulness of the language. I think in a future episode I'll be covering the more complex or challenging scenarios where what if you have multiple, right? What if a multiple reader and a single producer, right? And then this is when things get really tricky, right? Like you can have the readers lapsing each other, right? The readers, one of them catching up to the writer, but the other one didn't, and then like so on and so forth. Like what if one reader completes before the other reader, but there's more work to do, right? And then so you have a really slow reader, a really fast reader, right? And what happens, right? And then so again, right, the TLA Plus and the model checker will help you exhaustively identify all failing scenarios and make sure that your algorithm can address it under all circumstances. Okay, thank you for watching. Bye.